In this first part of problem number 8, we need to draw the fourth figure in the sequence. And of course, in order to do that, we will make use of any sequence that we can see that exists. So in order to be able to construct the fourth diagram correctly, let us study the three diagrams in order to make use of any pattern that may exist. Let us first consider the number of pins in the base. No, we are not saying the number of units. We are saying the number of pins that we have in the base. So we have 3 pins there. 1, 2, 3. In the next one we have 1, 2, 3, 4, 5 pins. Then we have 1, 2, 3, 4, 5, 6, 7 pins. Let us also look at the number of pins that will span the height of each triangle. So how many pins we have from the base to the height? 2 pins. 1, 2, 3 pins there. And we have 1, 2, 3 pins there. Finally, we have 1, 2, 3, 4 pins. So what do we imagine? 3, 5, 7, 9. 1, not 1, but 2, 3, 4, 5 pins. So 9, 5. The number sequence in the base is 3, 5, 7. The next number in the sequence is 9. The number sequence in the height is 2, 3, 4. The next number is therefore 5. Figure 4 should therefore have 9 pins in the base, and the height should span 5 pins. There we have it. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 pins. Then we have 1, 2, 3, 4, 5 pins. That's very nice. We will then proceed to have more fun in completing the table. Nice. If we can say solving a mathematics problem is fun. It is. So we are rewarded for having fun. Now we need to complete this table. And what will we do? Of course, in completing the table also, we make use of any pattern that may exist. So notice that we have consecutive natural numbers in the first column and also in the product of the third column. So in the product that we have in the third column, we have consecutive numbers like this, natural numbers, 1, 2, 3, 4. So we have 1, 2, 3. What do we imagine? That it should be followed by 4. It should be followed by 4. The other numbers are the same throughout. 4 is the only new number, and the others remain the same. So the other numbers are the same throughout. So we have 2, 2, 2. This will be a 2. We have 1, 2, 3. This will be a 4. 1, 1, 1. This will be a 1. And the result will go there. So 2, 4 is 8 plus 1 is equal to 9. And that goes there. What else do we do? Also, the number in the second column is the square of the number in the first. So we have 1 is 1 squared, or 1 squared is equal to 1. 2 squared is equal to 4. 3 squared is equal to 9. And what do we imagine? 4 squared is equal to 16. And what squared is equal to 100? 10 squared is equal to 100. And then what about the other one? 20. 20 squared is equal to 400. What about the n? Irrespective of the number, we will square it. This time we have n. The square of n is n squared. Lovely. Maintaining that the numbers in the expression are all the same with the exception of 1, that one is also the same as the number in the first column. So in all of these, what do we notice? That these are the same all the way down. These are the same all the way down. That is the expression. The expression that we are talking about is actually the expressions in the third column. So in the third column, in the expressions, these are the same, and we imagine will continue. These are the same. We expect them to continue, and we know that is 1, 2, 3, 4. It's increasing like that. But notice that there's a break in the table, so we do not have 5, 6, 7. However, we need not be confused by the break, because whatever number we have here, which is the one that is different from the ones that we have here and here, which is the only one that changes its value as we traverse the expressions downward, then we notice that this number that we have here is equal to the one that we have here. So 1, 1, 2, 2, 3, 3, 4, 4. So if this is 10, we should have 10 here also. But these numbers are the same. So 2 times 10 plus 1. And that is equal to 21. And we imagine the same thing here. 2 times 20 plus 1. And that is equal to 41. And we may just write down 2 times n plus 1. Or we may say 2n plus 1. And that completes the table. It cannot be difficult. Notice that all of these numbers are the same. All of these numbers are the same. This one is the same as the first one. This is the same as this. This is the same as this. Therefore, we imagine that 20 will go here also. And there's nothing to it. We have completed the table. That is a lot of fun. There's no rule that says that we need to complete the table row by row or column by column. As a matter of fact, as long as the table is completed, the examiners will not know the order in which we place numbers in each cell, and they do not mind. In situations like this, make use of the patterns and complete the table in the most efficient way. So this is a test of common sense more than anything else. And some candidate might get overtaken by the fact that they need to complete a table that has rows and columns, and they might want to complete row by row or column by column. It is not necessary to complete row by row or column by column, but to ensure that the table is completed and also that the answers are correct. Here we have a pair of simultaneous equations in which one is a quadratic, and we expect that in a particular case like this that we will have two sets of answers. But let us see what happens. Usually, but not limited to, substitution is what I would call the universal approach that we will take to such a problem. So the first equation has y written in terms of x. We may take advantage of this situation and use the method of substitution in solving the system. Y is already written in terms of x. So what do we do? Substitute the expression for y from equation 1 into equation 2. So take this and substitute into this equation. In equation 2, where we see y, we replace it with 8 minus x. So do that now. So this is the same. Y will be replaced by 8 minus x. The x is the same. And we have 16 on the right hand side. Next, we expand the brackets and transpose negative 16 to the left hand side at the same time. So expand, we have 8x and we have negative x squared. Also, we will transpose this negative 16 to be a positive 16 here, and we equate that to 0. Continuing, we combine like terms. 2x squared minus x squared is x squared. 2x squared minus x squared. That gives x squared. And this remains the same, and also this. Well, some candidates may recognize immediately that this is a perfect square. Therefore, the two factors are the same. So we have two equal factors. Also, the solution will give us two equal answers. Well, it is not appropriate to say that it is one, but that we have two equal answers. Right. Now, after arriving at the two equal answers, it does not make any sense that we substitute both of them because we are about to get the same answer. So all we need to do is just make use of one of them, and that we substitute into the easier equation, which is y is equal to 8 minus x. So where we see negative x, we replace that with a negative 4, and we have y is equal to 12. Very nice. So when x is equal to negative 4, y is equal to 12. And the other one will be the same thing. When x is equal to negative 4, y is equal to 12. So we do not need to write down those two occurrences. The other part of the problem required that we state given reasons why or whether or not the line that we have represented by this is tangent to the curve represented by this. What is a tangent? Everybody knows that a tangent is a line that touches the curve at one single point. It does not cross the curve. It touches the curve at one single point. My students know that. After the examination, they say that they did not do that part of the problem. And I say, why? Because a tangent touches the curve at one point. Therefore, we expect the solutions that we have for this equation to be equal solutions. Therefore, we have one point at which the curve and the line intersect. Or the line will merely touch the curve at one single point, which is what we have there. So the line is tangent to the curve because solving this pair of simultaneous equations is actually finding the points where the curve and the line cross each other. The fact that we only get repeated values, we have repeated roots, that's what we call them when the answers are the same. We do not say that it is only one answer that we get. We say that we get two equal answers, or the answers are represented or representing equal roots. So the fact that we only get repeated values, the two x values are the same, is an indication that the line merely touches the curve at a single point. If a line touches a curve only at a single point, then the line is a tangent to the curve at that point. This is a beautiful gesture by the CSEC examiners, requesting the explanation of something that is evidently present in the syllabus, but in an unusual way. It is not strange or difficult. It is just that we do not usually see one like this on the examination. That makes it unusual. Now we have our linear programming problem. We have statements, and from those statements we are required to write down linear inequalities that represent each one of those constraints. The number of orchids Y must be at least half of the number of roses X. So the number of orchids must be at least half of the number of roses. Nothing can be less than the least. A value must be greater than or equal to the least. It cannot be less than the least. It must be greater than or equal to the least. Therefore, we have what? Y is greater than or equal to half of x, because cannot be less than the least. Here is another at least. We have what? There must be at least 2 roses. So it is the same thing. At least must be greater than or equal to. Nothing can be less than the least. And, of course, the number, as we have there, represents the number of roses. So x, number of roses, x, is greater than or equal to 2. There must be no more than 12 flowers. What does that mean? No more than 12 means that it can be equal to 12. So no more means that the number cannot be greater. But it surely can be equal to. Surely it can be equal to 12, but not more or not greater. The number can be equal to 12 and it can be less than 12. So whatever we have, which is the total, x plus y, must be less than or equal to 12. Next, we are required to shade the region that satisfies all of the inequalities. The greater than or equal to sign in reference to that line indicates that the values may be on that line or above the line. Greater than or equal to. It can be on that line or greater than, that means above the line. So the greater than or equal to sign in reference to that line indicates that the values may be on that line or above the line. Any region satisfying that inequality must be above that line. That one. The value of x increases to the right. Any value of x that is greater than or equal to 2 should begin at x is equal to 2 on that line and continue to the right. So greater than is to the right. So we will begin on that line and continue to the right. Like this. What else do we have? X plus y is less than or equal to 12. The less than or equal to sign indicates that the values of x and y or any set of coordinates that satisfy that inequality should be on that line or below, because it is less than or equal to. Equal to on the line, less than below the line. So we begin on that line and any region that is below that line is also included. The region to be shaded is the one that is indicated by the 3 arrows. Right, so that region should be where? Above the line y is equal to a half of x. It should be above that line. At the same time, it should be to the right of the line x is equal to 2. And also below the line x plus y is equal to 12. So above this line, to the right of this line, and below this line. Right there. That is our region of interest. Next, we will write down the coordinates of the vertices of the shaded region. 1 is right there. Coordinate 2, 1. Begin here, 2, 2 units, 1 unit. The other one, 8, 4. And finally, 2, 10. To derive a function for the profit, we have to consider that the profit on the roses must be equal to the profit on each rose, which is $3, multiplied by the number of roses, and the number of roses will be X. To find the profit on all of the roses, we need to find the profit on each rose. As a matter of fact, the profit on each rose is given to us. We need to multiply that by the number of roses. So take the profit on each rose, 3, and multiply by the number of roses, X, 3X. The profit on orchids will be equal to the profit on each orchid, which is $4, and we multiply that by the number of orchids, and that is Y. So we have 4Y. Just like in any other thing, if you have pencils and you make a profit of $5 on each pencil, what will be the profit on 50? You take that 5 and you multiply by 50. It is the same thing, only that in this particular case the number of roses will be X and the number of orchids will be Y, and we multiply those by their respective profits, and the total will be, of course, the total of those two. The maximum value of the objective function is usually the one that matches the larger coefficient of the objective function with the largest ordinate. So let us take a look at what that means. Notice that the larger coefficient in the objective function is 4, and it is the coefficient of Y. Therefore, we need to find the largest value of Y among the coordinates, and that is 10. So this one will give the maximum profit, or should give the maximum profit. I've seen on only one occasion alone, where there's a defiance of this general rule. So if we think that we might not be 100% correct, we may eliminate this one and then work out the values with these two, and then use only the one that gives the maximum. The larger coefficient belongs to Y, and the largest Y ordinate is 10. So that is what we are making use of. And I am sure that our brains are not so shallow that in an examination we cannot work out all of the values and then see which one is larger and then put that down on our paper. Or, well, if we prefer, because the Chinese say that what? Short pencil is better than long memory. So if you prefer to write it down roughly and then make use of the one that gives the maximum profit, then that's an excellent way to go also. So in this objective function, we use this pair of coordinates and we substitute those values. The Y is 10 and the X is 2, and 3, 2, 6, 4 times 40 turns out to be $46. Now we are required in this particular problem to find the length RS. There is no information that is given by which we may conclude that the triangles are right angled. We therefore need to apply the sine rule and or the cosine rule in our calculations. First, we need to find RS. The triangle in which it is located has a known side and a known angle that are opposite to each other. This makes it a candidate for the application of the sine rule. The rule makes use of a side and the sine of the angle opposite to that side in the following way. So we have A over sine A and B over sine B. That is a statement of the sine rule, and it may be used in solving this problem because we have one known side and the angle opposite to it. So we know that the sine rule is applicable. A is the angle opposite to the side A and B is the angle opposite to the side B. So let us apply it to this particular case. So A is the side opposite to the angle A and B is the side opposite to the angle B. Of course, this may be written also with the sine of the angle up there and the line down here. But because we are attempting to find the length of a line, it is important, or not necessarily important, but it is better for us to write the statement of the formula or the sine rule in such a way that we have the unknown in the numerator on the left hand side. So put it into our particular circumstance. We have RS, which is the length of the side, over 48, that angle, is equal to what? 7 over 60. So side, sine of opposite angle, side, sine of opposite angle, and then we may transpose. So transposing, multiplying by sine 48 in eliminating this denominator of 48, of sine 48, we have 7 sine 48 over sine 60. You have your calculator scientific, you just put 7 sine 48 divided by sine 60 and equal, and you get 6 centimeters in one step. It is not quite often that we are confronted with this situation. Its infrequent occurrence might render it unfamiliar, but its uniqueness leaves us no doubt as to what to do. So we are giving and taking here. One advantage, one disadvantage. When all of the sides of a triangle are given and no angle, then we know that the cosine rule is applicable. So we do not think about any other thing except cosine rule, because we do not have any angle. If we do not have any angle in a triangle, the cosine rule is the only one that can be used. And that sets it apart from the others. So we are sure that immediately it is the cosine rule that we need to use in finding the angle that is located at T. So while throughout the years, if you follow the CSEC examination, you may find cases in which you can apply the cosine rule, as we are applying it here. And some students prefer to use the cosine rule than the sine rule at any rate. And we may find circumstances in which a correct application of the sine rule can give you an incorrect answer, because the cosine of an obtuse angle is negative, while the sine of an obtuse angle is also positive. So when it pertains to obtuse angle and so on, the difference between obtuse and acute, in finding an angle, it is more appropriate for us to use the cosine rule. But it is not often that the situation is a must, which is in this particular case. So although we do not have this situation coming up quite often, although we may use the cosine rule in situation that we do not have to use it, but in this particular case we have to use the cosine rule. It is not often that we find a situation like this, so that might cause it to be, the circumstance to be unfamiliar. However, its uniqueness, as we said before, leaves no doubt that it is cosine rule that we need to apply. And this is a statement of the cosine rule that we are applying, and we'll take a look at what these details mean. There we have it. We need to find QTS, which is the angle located at T. The two sides in the sum, which we have right here, will be what? The two sides that form the angle T, 8 and 10. And this one, which is the one that we subtract, is the other one, which is the one that is opposite to the angle T. And again, we have the two sides B and C. Those are the two sides that form the angle. So we know that the two sides that form the angle will go here and here, will go here and here, and then the other one, which is the one opposite to the angle, will go there. So in our substitution, we have no difficulty. There we go. Another step of simplification. And then finally, cosine of t is equal to 0.719, and we will find t by taking the cosine inverse of 0.719, and that turns out to be 44 degrees. I'm not that good. I just remember the answer, that it is 44 degrees. What are we required to do here? And how are we about to do it? While finding OUZ, which is what we need to find, OUZ, this angle, let us calculate some relevant angles that may also be relevant to other sections. And I'm sure they are relevant to other sections. Let's go. Triangle OUZ is isosceles. Why? Because it is formed by the radii of the circle. So it is isosceles. That makes these two angles equal. So take away that 70 from 180, then we divide the result by 2, because all of the angles in that triangle have a sum of 180 degrees. And the other two angles are equal, this triangle being isosceles, 55 degrees. Angle subtending a diameter is equal to 90 degrees. So this is a diameter because this passes through the center of the circle. So there we have it. This is our diameter. These are the other two sides. The angle is 90 degrees. That angle, this part is 55. So we need the rest of that, which is OUZ is the rest of that angle. So angle subtending a diameter is equal to 90 degrees. OUZ is the rest of that 90 degrees. 90 minus 55 is equal to 35 degrees. So OUZ is actually 35 degrees. In finding UVX, let us make use of the fact that triangle UOZ is isosceles. We are finding UVX. UVX. That's the angle that we are finding. Let us make use of the fact that this triangle is also isosceles, being one that contains two radii. So this triangle is also isosceles. So what do we know? That is also 35 degrees. And we are making use of that in finding the angle UVX, which is which one? UVX. Also, angles in the same segment are equal. Angles in the same segment are equal. So we have, this is the segment, that big segment there, what we call the major segment. This is the chord. These two angles span the chord at the circumference. There we have the other one, spanning the chord at the circumference. So these two angles are equal. They are equal to 35 degrees. How important is that in finding UVX? UVX. UVX is one angle in a right angle triangle because tangent and radius meet at right angle. Right, so we have this triangle is a right angle triangle. This is a tangent. This is a diameter. So this part is a radius. So the radius and the tangent meet at 90 degrees. Therefore, this is a right angle triangle. 90 degrees will be here in this right angle triangle, and this one is 35. So we know that because it's a right angle triangle, the other two angles, this one and this one, have a sum of 90 degrees. So UVX is equal to 90 minus 35, which is equal to 55 degrees. Continue. UWO is inside of that large triangle in which it is the only unknown angle. We need to find UWO. UWO. I guess the examiners are probably trying to catch us on one foot, with one foot on the ground, by not asking us to find UWZ. But UWO. Maybe it would have been easier to say UWO than UWZ, and at any rate, because we have this right angle here, and this is 70, and this completes the angle. So there we have it. So UWO, which is the angle in this triangle, this is 35, this angle completes the angles in the large triangle that we have there. This angle subtracted there, this one subtracted here, and this one and there we have our answer, 20 degrees. We need to find out in the next section, the ones that we are actually working on, the triangles that are congruent to two triangles that are given. But what do we mean when we say that triangles are congruent? So if two triangles are congruent, then they are equal in all respects. But how do we show that two triangles are equal in all respects? One minimum requirement of congruence is that there should be a one-to-one correspondence with the angles of the triangle and a single occurrence of corresponding sides that are equal. So both triangles, let us use an argument, both triangles should have equal 30 degrees angle, then equal 60 degrees angle, then equal 90 degrees angle. In addition to that, we should have corresponding sides being equal in length. If we can find two cases in which angles are equal, then that should suffice, because their third angle will be the rest of 180 degrees in each case, and will therefore be equal. Which triangle is congruent to ZOU? Let us take a look at what we said before and what it means. If we need to have all three angles being equal, if we can find that one is 30, the other is 30, one is 60, the other is 60, then in each case, the other angle that remains is 90, because we take away that sum from 180. Therefore, if we have two pairs of angles that are equal, then we have the requirements of all angles already. All we need is a pair of sides, corresponding sides, that are actually equal. So which triangle is congruent to ZOU? ZOU is that isosceles triangle that we have right there. So the triangle is isosceles, and we are proposing another isosceles triangle to be congruent to it. And what is that isosceles triangle? That one that we have right there. Are they congruent? Surely they are congruent. It is easy to see that they are congruent because we have 35 here, 35 here, 35 here, and 35 there. We are sure that these angles being opposite to each other are equal. And of course, this is a radius of the circle, and this is a radius, this is a radius, and this is a radius. We far exceed the requirement for congruence. All of the angles must be equal because this is 35, this is 35. These two are equal, being opposite angles in intersecting lines. And then we know that these are all radii of the same circle. Those are congruent. That means those triangles are congruent. Since they are isosceles, all of those acute angles are equal, and in each case, two of the sides are radii of the circle and are therefore equal. Finish. So this is an isosceles triangle. This is 35. This is 35. This is 35. This is 35. These two are equal, and these are radii. Those are congruent. The third angle of each triangle is fixed because the acute angles are known. Not only that, but we know that these are equal, being opposite angle on intersecting lines. There is therefore no doubt that the triangles are congruent. All of these are radii of the same circle. So the one that is congruent to ZOU is OXY. For the triangle that is congruent to XYU, I am proposing XZU. So we have X, Y, U, X, Z, U. We are proposing that those two are congruent. But are they? Based on the fact that the two previous triangles are congruent, then we know that UZ must be equal to XY. So UZ must be equal to XY because the previous two triangles are congruent. So we have no difficulty with that. So all we need now to do is to show that two pairs of angles are equal, and we are done. So those two sides are equal, and they are corresponding sides of the two triangles. All we need to do now is to get two pairs of equal angles. Also, at the points of the Pope's hat, we have those two 35 degrees angles. There. Those two 35 degrees angles at the point of the Pope's hat. This looks like a Pope's hat. Also, we have these two corresponding angles are equal. This is the sum of 35 and 55. This is the sum of 35 and 55. And we may also see these angles are angles that subtend the diameter. So this is the diameter, and this angle subtends the diameter. So it is a right angle. And also this diameter here, these two angles are spanning the diameter. They have a sum of 90 degrees, therefore it is not difficult to see that they are right angle because of the other purpose, not because of their sum that we can see right here, but because they span the diameter. They are also right angles. So we are finished. There are more than enough facts by which we may conclude that the two triangles are actually congruent. Therefore, the one that is congruent to XYU is UXZ. In this section, we are required to find the two vectors and show that we are capable of answering the rest of the problem. By the triangular law, because we are required to find BA, by the triangular law, BA is equal to OA minus OB. So BA, we have OA minus OB. We have OA right here, we have OB right there. All we need to do is subtract 6 minus 3 is 3, 2 minus 4 is negative 2. That's all there is to it. So BA is 3, negative 2. And we are also required to find what? BC. BC is equal to OC minus OB by the triangular law. And we have 12 minus 3, that is equal to 9, and negative 2 minus 4, that is equal to negative 6. In this section, we need to write down one relationship between the two vectors. It is obvious that BC is equal to 3 times BA. BC is equal to 3 times BA because we have 3 to 9, negative 2 to 6. 3 is 9. 3 negative 2 is equal to negative 6. So this one is actually 3 times this one. Whenever we can write vectors as products of each other, as in that manner, we know that they are parallel. The vectors are therefore parallel. So we are concluding that the vectors are parallel. They are parallel because whenever we can say one vector is so many times the other, it means that they are going in the same direction, but the length of one is 3 times the other. So they are parallel. Now it is required that we draw a sketch and show the relative positions of those points. In showing the relative positions of A, B, and C, we need to consider that B is a common point of the two vectors. B is a common point in the vector BA and BC. The vectors are in the same direction because the components have the same sign. Notice that we have a positive 3, a positive 9, a negative 2, a negative 6. Therefore, the vectors are going in the same direction. So we are sure of that. And the common point is B. B is the common point of both vectors. Let us show that point first. There we have B. What else is said? BC is greater than BA. Remember now that they are in the same direction. BC is greater than BA. Therefore, C is further from B than A. In other words, A is located between B and C because C is further from B than A. That is where we have A. Because BC is equal to 3BA, A is not a bisector of BC, but somewhat closer to B than C. Because BC is equal to 3 times BA. So A is not a bisector of BC, but somewhat closer to B than C. As a matter of fact, BA is 1/3 of the distance BC. We do not have to place A exactly 1/3 the distance away, only obviously closer to B than C. So A should not necessarily be placed exactly 1/3, but a little bit closer to B than C. That is more indicative of their relative position. Right. As a matter of fact, it is not necessary to actually place A a little bit closer to B or to C or go through that rigmarole or detail, because only the relative positions we need. So placing A between B and C will suffice. There we have a matrix product, and in that product we have two unknowns. To find the values of A and B, of course the two unknowns, we need to equate the appropriate sum of product to its associate value in the resulting matrix, and this is the resulting matrix. So what do? Take a note of that result, which is the value is at the upper left. We will multiply the upper row by the left column. So because this is at the upper left, we will multiply the upper row by the left column. And what do we get? A times 2, negative 4 times 1. So 2A, as we have it right there, 2A plus negative 4, or 2A minus 4 is equal to 2. So those two are equal. 2A minus 4 is equal to 2, and we may solve that. 2A is equal to 6, transposing that by addition, and then A is equal to 6 divided by 2, which is equal to 3. Do the same there. We have that one is located at the lower right. So the value is at the lower right. We will multiply the lower row by the right column. The lower row by the right column. 1 with negative 4 gives a negative 4. B with negative 3 gives negative 3B, and the result is 2 again. So transposing this negative 4 by addition again, and then say 6 divided by a negative 3, B is therefore equal to a negative 2. B is equal to a negative 2. We will continue by solving the other part of the problem that requires us to write down the inverse of this matrix. We will be writing down the inverse of this matrix. And what are we making use of? Because hence or otherwise, write down the inverse of this matrix. That's what the problem says. Therefore, we should be able to use this fact that the result is 2002 to just write down the inverse of the matrix. Otherwise, we will go through the length to determine the inverse of this matrix, because it can definitely be done. The matrix is equal to 2 times the identity. Now we multiply this matrix by this matrix, and the result is 2 times the identity. This multiplied by this, the result is 2 times the identity. And we also know that when we multiply a matrix by its inverse, we get the identity. Therefore, if this is 2 times the identity, that means this one of the matrices is 2 times the inverse. Therefore, we will have to divide that matrix by 2. So a matrix times the inverse gives the identity. But in this case, we have 2 times the identity. Therefore, one of the matrix is 2 times the inverse of the other. So if we have this one, then this matrix is 2 times the inverse of this. Therefore, to find the inverse of this one, we will have to divide this by 2. Therefore, one matrix in the product is twice the inverse of the other. The inverse of one matrix is therefore a half of the other. So in order to write down the inverse of this one, we will take half of this matrix, because this matrix is twice the inverse of this. The value that we have here is a 3 that should really be here, and a negative 2 that should really be here. So taking a half of 3, we get 3 over 2, and taking a half of this negative 4, we get negative 2. Taking a half of this, no difficulty, and taking a half of what? Negative 2, we get negative 1. No problem. Next, we are required to use this inverse to solve this equation. Therefore, in solving this equation, we should multiply actually this side by the inverse of this matrix, which will eliminate the matrix from this side, and we need to do that on the other side also. Therefore, we have xy is equal to actually the inverse of this matrix multiplied by 12, 7. However, we did not want to manipulate it with the fraction, so we just took the half outside for now, and then use 3, 4, 1, negative 2, and take the half outside, just to avoid manipulating the fractions too early. Then what do we have? Multiplying this, we get what? 3 12s, negative 4, 7. 1 12, negative 2, 7. And 3 12s, 36, minus 28. And what is the result? Also, we have 12 minus 14, and that is negative 2. We will finish up by taking half of the results. So x is actually equal to 4, and y is actually equal to negative 1. A matrix times its inverse is equal to the identity. If the product is twice the identity, then one matrix is twice the inverse of the other. As we said before, to find the inverse of any of the matrices, we simply find half of the other. So to find the inverse of this, we find half of this. To find the inverse of this, we find half of this. But we were required to find the inverse of this, so we did that by taking half of this one.